let's do an example. Let's say you had a problem that was f of x, and it says 2 here, and then x plus 4 squared minus 3. And then on the assignment it does this, then they ask you, well, what do all those numbers do into the problem? Well, it's a squared graph. I put the little squared on the outside of the parentheses. So that little 2, some people ask, what does that do? That really does nothing except it tells us that it's a quadratic graph. It's a quadratic graph like one of these parabolas. When it has the second power in it, it just tells us it's that kind of graph, the parabola, the quadratic. So what do you think the number at the end of the problem does? Do you know which way that would move the graph? Yeah, that'd make it go down 3. What if it has a number in here? It says plus 4 inside the parentheses. Yeah, it's the opposite, so you go left. This one's left 4. It says plus 4, but you think like, oh, that's minus 4 to the left. You think opposite. Yeah, so try to remember the one inside is like opposite. If it says plus 4, you actually go minus 4 to the left. And then, what about the 2 at the beginning? Yeah, they call that a vertical stretch. And if you have to graph it, well, it shouldn't be too bad. It's just like, okay, I go to a graph. I have to go left 4. 1, 2, 3, 4, you said. Down 3. You just move and do these last 2 things first. Go left 4, down 3. And then the vertical stretch thing, I tell people to like start at that center spot that we already went left 4, down 3. I just tell people to go up 2 over 1. Vertical stretch. So it makes the graph a little bit skinnier than the normal parabola. The vertical stretch part makes the graph kind of skinny. The vertical stretch makes it kind of skinny. So the first number is a 2, so that just tells me like go up 2 over 1 each side, then you get kind of a skinny graph out of it. So that's how you can just do it kind of quickly and get it graphed. You shouldn't have to sit and make points all day long, you know. You could just quickly graph it. These numbers actually give you like the vertex, right? This is called vertex form. So the vertex is -4, -3. See, the vertex of your graph is from these numbers. When you said left 4, that's -4, and then down 3. You know, those numbers give you the vertex, just so you know. Most of you guys already know that stuff. Okay, now there is, besides moving left, right, up and down, vertical stretches, there is sometimes reflections. You know, like flips over different graphs. So we'll do a couple reflections too and show you those. Hi. Oh yeah, he's right here. Yep. Okay, let me go to, I'll write down reflections next, okay? Okay, reflections. There can be different kinds of reflections. Reflection is when a graph flips. So I'll do like an example with a square root graph. Like y equals square root of x. There can be reflections where a reflection is where they put a negative sign in the problem. And if their negative side could be like way in front of the entire problem, or it could even be a negative like inside the square root box. And these would do different things. So the first graph is just the normal square root graph. The normal square root graph, it looks like that. You know, that's just the normal one. So what would happen if they put a negative in the front of the problem? Yeah, it depends on if it reflects over the x-axis or the y-axis. That's right. Good job. So if it has a negative in front, that's a reflection or a flip. It's a reflection over the x-axis. But if the negative's inside the square root box, then the reflection's over the y-axis. Reflection over the y-axis. And it's important to recognize that because on the assignment, they give you, either one or the other, and you have to figure out which one it is. So if it reflects over the x-axis, that means it kind of like flips down. So if I graphed it, it would like flip down like that. If it has a negative in front, it would like flip downward over the x-axis. But if the negative's inside the box, like this one, then it flips over the y-axis, and instead of like going to the right, it goes to the left. The arrow points to the left. Because the y-axis is this up and down. So you flip it and it flips, instead of pointing to the right, it points to the left. Yeah, so the first one's kind of like an up and down, flipped it down, but the other one, this one flips it left and right. Flipped it that way. So those are the kinds of reflections you can get. So, and it can get tricky, the more numbers they add in the problem, it can get tricky. So let me do let's do like a whole example. Like, what if it had y equals square root negative x plus 3, and then I'll do like plus 1 at the end. Okay, when the one that I think the trickiest one is the one where the negative's inside the box, like this last example, like this third one. When the negative's inside the box, it can be kind of tricky. And now that they added a number in there also, inside the box, inside the radical, you have negative x plus 3. What I would suggest is this part right here. I would suggest to factor out the negative. Because that negative in front, surprisingly, it actually affects like the left and right shift too. Factor out this negative. So what I mean is, I'll write it over here on the side, like y equals, and you have this square root thing. Like, put the negative, pull it out away from the x and the 3. You know what I mean? That's what factoring out means. Like, take it out, separate it, pull it out, and have a parenthesis. If you took a negative out and pulled it away from that x, inside the parenthesis, what would we have?
X plus 3.
Yeah, it would be x minus 3. You factor out a negative. Like, it's like flip the signs. It's like take out this negative so it's just a positive x, and then the positive 3 turns to negative 3. Why am I telling you to factor it out? Because this is the reflection part. The negative is the reflection part over the y-axis, right? And then usually the part inside tells you like the left and right shifts. So now it's kind of clear it's separated from that reflection. And we have this part. Does that make it go left or right? X minus 3. Which way is it? Yeah, remember it's opposite, so it actually goes right 3. Even though it says minus 3, it goes right 3. And then the plus 1, that would be up 1, right? So the ones that have the negative inside, right by the x, inside the square root, or inside the print, you kind of have to figure it out. So you take that negative, because then you get, otherwise you'd get this part wrong. The left-right part, you'd get it mixed up. So it's kind of tricky. All right. So reflections and translations, that should be kind of familiar to you from Algebra 2. The next part, it has some different things that you might not be as used to. The 2.6 part of the lesson has you combining functions and doing composite functions and finding the domain. And the domain seems to be kind of a tough thing for some people to figure out. Find the domain. And it's not finding the domain from a picture. It's finding the domain from an equation, you know. Find a domain of a function. And it has combining functions and composite functions. Those are the kind of topics in this section. Combining functions is actually pretty simple. That's just like adding things together or subtracting or multiplying or dividing. The combining functions part of it won't be too bad. But the composite functions, that's when you do like f of g of x, like plug an equation into another one. A composite is when there's like a function inside another function. Like you plug one function into another. So we'll have to go over that part. So earlier this year, we've already found domain and range, but we've always looked, a lot of times you just look at the graph and say, what's the domain of this picture and what's the range of this picture? Well, now it's not going to be a picture. They're just going to say, find the domain, and they'll give you an equation. Find the domain of f of x equals square root 3x plus 12. So this time it's not a picture. See, it's not like find the domain of this picture graph. It's find the domain of this equation. Well, you have to think about what we know about square roots, what we've learned in the past about square roots. Can you take a square root of a negative number? Yeah, it won't give you a real answer, it'd give you an imaginary answer. So we've learned how to deal with it. But yeah, usually if you have a square root of a negative, it's called imaginary, and you put I. So if you're thinking of graphing it, I want to graph all the real numbers. We're not going to graph imaginary stuff. So we've talked about how the part in here, since we can't take square root of negative numbers, the part in here has to be bigger, has to be positive, obviously, then. So this part inside of here has to be greater than or equal to 0. Because you can't take square roots of negative things, so we want whatever's inside the square root to find the domain of square root functions. That part inside of there has to be greater than or equal to 0. And then you could just solve that to find your domain. So you could subtract 12, just like a regular equation. 3x greater than or equal to negative 12. Divide by 3, divide by 3. X is greater than or equal to negative 4. That's called set builder notation. This is one answer. This is set builder notation. But sometimes on the homework, they're going to ask you for that interval notation. So I got the answer, but how do you write it another way in the interval notation? This means you're on a number line. Here I'll just draw here's negative 4, negative 3, negative 2, negative 1, 0, 1, etc. Okay, what does this mean? Which numbers does this graph hit if I was going to graph it?
Negative 4.
What else? Does it go to negative 5 or negative 6, or does it go negative 3 to...
Negative 3 goes that direction.
Yeah, it's greater than, so it goes this way. So how do you write that in interval notation? You guys remember? We just had it a lot in that last... You remember, Midhani?
Bracket, negative 4, and then parentheses, positive infinity, and then just normal parentheses.
Yeah, there you go. It just means, yeah, this is the interval way to say it. It goes from -4 and it goes up. So it goes up forever. You go to infinity. Yeah, so when you do your assignment, they will ask again, I think quite a few times for the interval notation. So if you have a square root graph and they want the domain, just take the part under the square root, say it has to be greater than or equal to 0, and that'll give you your domain. What about a fraction problem, like a rational function? And it'll say find the domain. And what if I give you a graph or a problem, that says f of x equals 3x plus 2 over big fraction x squared minus 2x minus 3. See, it's not a picture, but I still want you to tell me the domain. And I don't have the picture graph for you. So how are you going to figure out the domain of this graph, of this function? So in math, you can't divide by 0, right? Yeah, that's so, Kenny, you're on the right track. You cannot, in math, you cannot divide by 0. If you try it like on a calculator and takes anything divided by 0, it says divide by 0 error. So it would be like bad if the bottom of this fraction equals 0. It'd be bad if you was dividing by a 0. In math, it's bad. So if you figure out equal the bottom of the problem to 0 and try to solve that, factor it, factor the denominator, you could figure out what are like numbers that are not in the domain. So how do you factor x squared minus 2x minus 3?
X minus 2, x minus 1.
X minus 3, x plus 1. Okay, so if you equal those to 0, x minus 3 equals 0, x plus 1 equals 0. If you equal those to 0, you get positive 3 and negative 1, right? Those numbers are not in the domain. Those would be like bad answers. Those would be like something where if 3 was one of the numbers you plugged in, you'd get dividing by 0. It would make the bottom of this problem equal 0, and that would not be in the domain. So yeah, it's like x is not equal to 3 and x is not equal to that. So x could be anything else. Like again, if I drew a number line, it's saying like our answer, here's 0, 1, 2, 3, here's 3, here's negative 1. I'll just put a few numbers on a number line. Okay. So we're saying like the answer to this graph, if this function, if you graph it, you cannot have 3 and you cannot have negative 1, but anything else works. Everything else is actually a good answer for the domain. If you did graph this problem, these are places where the graph has like asymptotes. I could just sketch it really fast, just so people know. If you took pre-calc last year, a lot of you are familiar with this, but not everyone has taken pre-calc, and that's fine. Not everyone has taken the same math classes. So these numbers, this 3 is one of the answers. It'd be a place where the graph has a, place where the graph doesn't hit. I'll move that over. And the other answer was what, negative 1? That's another place where the graph would have an asymptote. And it's like if you graph it, I'm not sure exactly what it looks like. It might be something like this where it has a curve over here. I don't know because I didn't look at it that closely. It could be a thing where you have like curves around those lines, but the graph never hits those lines. They're called asymptotes. So yeah, these are problems that are not, these two answers are not in the domain. But everything else is. You can hit any other number is good for this answer. So the way they want to write it again is interval notation. And on the assignment, that can be kind of tricky to say you want all the numbers except these two numbers. So the way they do that is, you see how I kind of graphed it for you on a number line. we can go down as far as we want. You can go down to negative infinity, and you can go up to the number -1, but not include that number. So the interval notation would be saying like, well, you could have any number lower than -1, and then they do the union thing. You'll see it on your assignment. Then they do union, because then they say, well, it could also be some more answers. There's more parts to this. Another answer could be a number like between the -1 and the 3. So -1, comma 3. You could have any number between those. And then do a union again. And the other part of the answer is numbers greater than 3, right? Like all these numbers greater than 3 on the number line. So 3 to infinity. That would be the interval notation answer. That's what they would want. That's what they would want for the answer, all that on the computer. They want interval notation. So that's how you say, see, it's like hitting all the numbers. Numbers lower than -1, up to -1, numbers between -1 and 3, and numbers from 3 to infinity. That's how they say it in interval. I know that's long, but hopefully you kind of see it's just lower than that number, between those numbers, and then the numbers higher than that.
So we just put ranges, we don't put any close parentheses like the boxes?
Yeah, there's no squared off brackets here because we're not including those. Yeah, because those are open circles, so it's just parentheses. Yeah, so finding the domain can be kind of tough. So things you have to watch for is like a fraction. You just set the denominator equal to 0 and solve. Yep, those are the excluded values. Yep. What about other just problems like find the domain of, what if you have f of x equals 3x squared plus 2x minus 1? What if you had a graph like that? Or f of x equals 4x to the third plus 2x squared minus 4x plus 5. I'm just making stuff up, but what if you had graphs like this and they say, what's the domain? This one's a quadratic. This one's just another like polynomial function. These are polynomial functions. Do you know what the domain is of these? They have the same answer actually. Yeah, the domain of these, just to kind of go over it, is negative infinity to positive infinity. Yep. Just so you know, like any polynomial function has a domain negative infinity to positive infinity. Or a quadratic. The domain of quadratics is negative infinity to positive infinity. What about like a linear equation, like a y equals mx plus b? What about one of those kind, like y equals 2x plus 4? What about a linear equation? What kind of domain does it have? Just so you kind of know, like the different kinds of graphs. And this is a linear equation. You know, just a line, a linear, y equals mx plus b, something like 2x plus 4. Yeah, Medhani, you're right. It's the same. The domain and range of that's negative infinity to positive infinity. Yeah, so like straight lines go on forever. You know, like lines go on forever. So it's linear. So you should be kind of able to tell when you have polynomial functions or just lines, your domain's negative infinity to infinity. But you just have to watch for like square root graphs. The part in the square root has to be greater than 0. And fractions, you can't divide by 0. So the domain of this, you just have to look at the denominator, set it equal to 0, and the graph can't hit those numbers. Okay, and then finally, we're spending a bit of time on domain, but because it's kind of a tough concept to figure out. Now the rest is going to be combining functions and composite functions. Combining functions, let's talk about what that is. Well, they're going to give you like two functions, like f of x equals 2x minus 1. And then they'll give you another function like g of x. And it is 5x plus 3. Okay, so I have an f of x problem here. And this one, they call it g of x, just a different letter. Starts with a different letter just so you can tell them apart, f of x and g of x. So what if I told you to figure out f minus g of x? This is what combining is. Combining is going to be either adding the problems together, subtracting them, multiplying them, or dividing them. So I wrote it f minus g of x. So what's that telling you to do? Let's just subtract, right? So how do you do f minus g of x? They're just telling you to take the f problem, this problem over here, that says 2x minus 1, take that one, 2x minus 1, minus the other one that says 5x plus 3. The thing you got to be careful with the minus, the subtract, is that it's minus both of these things behind it. You have to distribute your negative. People forget about that. It's minus 5 and minus this last 3. You have to distribute your negative. That's just the things people forget, just little things.
Is there an X on
Why is there an X where at?
the outside, where it says F minus G of X?
F minus G of X. Okay, this is how they write it. They're saying you have an f of x function and a g of x function. They're telling you to subtract them, and it's f minus g of x. It means it's still like a function of x.
Okay.
It just means like it's still a function of x. So they'll have like f plus g of x or f minus g of x. Yeah, they just put the variable at the end. They're just functions with x in them. Yep, they're just functions with x in them. So this is what they'll ask you to do right here. I'll just box it in. And it's just trying to tell you, take these two functions and subtract them. And they're functions with letter x's in them. Yeah, functions in respect to x. So yeah, we take the 2x minus 1 function and the 5x plus 3 function over here and just subtract them. So don't forget that you have to distribute this negative. You have this 2x minus 1, and then it's minus 5x, and then minus 3. People just forget about it's minus both of these things after it. So what do you get for the answer? Yeah, negative 3x minus 4. That's the answer. Yep. So that's f minus g of x. That's the answer for when you subtracted those two things. Yep. That's the answer. Again, they might at the end even ask you, what's the domain now? What's the domain of this new function we put together? What's the domain? What do you think the domain is of negative 3x minus 4? What kind of graph is it? Like, is it one of those parabolas, or what is it? Yeah, it's linear. So the domain is negative infinity to infinity. Linear graphs, the domain and the range of linear graphs is negative infinity to infinity. Yeah, so just kind of have to know that. Okay, so this one was subtract f minus g of x. What if they ask you to do fg, like this, fg of x? What does that mean? Yeah, I just wrote fg. I didn't put anything between them. So isn't that times? Yeah, multiply. So the first problem f was 2x minus 1. And the second problem was 5x plus 3. This time it's multiply. Yeah, when it's just FG written together, that means multiply. Yeah, so they ask it like this. They ask something like this, find FG of x. That means like multiply the f and g functions together. Well, we've done this before. You have to distribute all this out. FOIL, first, outside, inside, last. So you're going to have to multiply those out. So 2 times 5, that'd be 10x squared. Then you do the outside, you get 6x. Inside, negative 5x. And last, negative 3. So I'd get 10x squared plus 1x minus 3. Okay, so I got my answer. And then again, just so you know, they could ask you after that you do the math and add the stuff up or multiply the things together, they might ask you the domain again. So I got my answer right here. What's the domain? Yeah, it's negative infinity to infinity again. If it's just a linear equation or problem, this one's a quadratic. Yeah, those have domain negative infinity to infinity. Okay, finally, composite functions. A composite function is a little different. Okay, so let's write the problems down again. Let's say we have f of x equals 2x minus 1. And then I'll do a different one for g of x this time. G of x, let's say a g of x problem could be x squared plus 5. Okay, let's do a composite function. What a composite one is like where you take one problem and put it in the other. They write it f of, it's a tiny circle. It's not a time sign. It's a tiny little circle, and so they say f of g of x. That's how they would write it. It's written like this in the books. It's not a dot times. It's saying f of g of x. F of g of x. That's how you would read it. Like how you would read it, they say f of g of x. I know it's kind of weird how they say things, or how they the notation for things. F of g of x. That's how you would like read it yourself. F of g of x, like quotes. There we go. Another way that you might see f of g of x written is f parentheses g of x, like this. This is the same. These are the same thing. It still means f of g of x. I kind of like it this second way better. I like writing it the second way because I can see that the g of x problem is like inside a parenthesis, and that's the one the innermost problem, and it's going to go into the outside function. Like here it's more like you have this inside, g of x, and you start on the inside, you like start with g of x. Okay, so I would say like for little notes, you would start with g of x. Like look at the g of x problem. What's the g of x problem say up above? I know it gets kind of confusing. So which one's the g of x function? So you start with this x squared plus 5, and what you do with it, you take that problem, start with g of x, and plug it into the other problem. Plug it into f of x. Like, you're going to take this, because it says g of x inside, and you're going to take it, and go over here and go to the f of x problem and like plug it in. Plug it in for x. That's what it is. You like take this and plug it in over there. That's what f of g of x means. You take the g of x problem and you go over and put it in the outside function, the f problem. So then you rewrite it. So f of g of x, what does it equal? All right, so what's the answer? Well, it's going to be, see the 2, it's going to still say 2, and then you're going to put this in there. You're going to put in x squared plus 5 minus 1. That's what composite functions do. You like take a whole problem and plug it into the other. So what do you think of that? It's not too bad, just like knowing. It's different than this one. This one is times, but this one has a little O, like a little circle, f of g. Means like take the g problem and plug it into the f1. Then they expect you to kind of clean this up a bit, distribute this out. So it'd be 2x squared plus 10 minus 1. So it'd be 2x squared plus 9, right? And that'd be the answer. So yeah, you like take a whole problem and plug into another one. That's what composite does.
Is it kind of like when you're doing equations and you're using elimination?
Yeah, it's kind of like substitution, like substitute a whole problem into another one.
If there were 2 x's, would you plug it into both?
Yeah, if this was 2x minus x, I would have put 2 times this stuff and then minus this stuff again if that was like an x at the end. Yeah.
And so you only
Yeah, if there's more than one x, you'd put that into both of the x's. Yeah.
How do I know which number goes in and which number stays out? Is it the first number that, like, how do I know that g is going inside of f and not f going inside of g?
Because the g part was like second, the g of x, you put the g of x problem into the f problem. If they wanted you to do it the other way, they would have put g of f of x.
So the order matters.
Yeah. If they would have had it g of f like this, if they would have had it g of f of x, yeah, then I would have took this problem here and stuck it into that one. Then I would have done 2x minus 1. I would have took that and put it in here and squared it. I would have wrote 2x minus 1 squared plus 5. And then I would have tried to work that out. Okay, so that covers everything. I know that's quite a bit, but yeah, the composite function is like take a whole problem and plug it into the other one. Okay, so we can just work on our problems now, work on our assignment. I can come around and help people.